today on the agenda, you can see we're going to go over some notes of motion vocabulary. A lot of the terms are terms you're familiar with, terms we've talked about. Some have been defined in the worksheets you've done. But I want to give you a formal definition and practice some problems as we're really done with everything for this Unit 1A. And so that's why we're having our test next week. But I want to make sure if there's any terms that weren't clear before, that hopefully after today they will be. And then once we're done going over those notes, you're going to have probably about half the period, maybe even a little bit more of time to work on getting your lab reports put together. So making your graphs, summarizing your data, doing the extension questions. And so you'll have quite a bit of time today to put some work in on that side. Again, a couple reminders. If you haven't turned in the Pendulum Lab corrections yet, the deadline is tomorrow. And we don't have class tomorrow, and I just mentioned to you guys that I won't be here tomorrow. So if you bring it, just come and sit it on my table over here, and then when I'm back over the weekend, I can grab it and take a look and have it ready for you on Monday. So yeah, just you can still turn it in tomorrow, even if I'm not here. So if you come in, well, if my door's closed, if it fits, just slide it under the door. If it doesn't fit, the core room is right downstairs, right below, like it's just right here. And if you just walk down the hallway to the core room where all the teachers' desks are, mine's in the back left corner. You'll see a bunch of Dodgers bobbleheads on top and a basketball and some stuff. So you can just, if you can't slide it under the door, you can just put it on my desk back there. It's fine to go back in the corner. You can just, there's usually a teacher back there working, and you can just plop it on my desk there. So you could also just show me in class today, because like I said, you're going to have a pretty good chunk of time to work on your lab report. So if you just want to show me in class today, I can just do the update right here while we're together. So either way, for quiz retakes, I do have a pretty good group of students today taking a retake during lunch. So if you want to join them, you may. I'm not available after school today. And then, like I said, I won't be here tomorrow. Next week, there's not really a set lunchtime on Monday because the Monday schedule's weird, but if you have a free period that matches with mine, you can try to schedule that with me. I have another doctor's appointment Monday, but that's the only one next week. So then Tuesday, Wednesday, Thursday, Friday next week, during any lunch or during any day after school, as long as you schedule ahead, you can do a retake then. But so corrections for the lab due by tomorrow, but quiz retakes still can do all through next week. Do keep in mind that next Friday, we have our Unit 1A test. So you probably don't want to wait and do that retake on Friday when you're off. Well, I guess for you guys it'll be Thursday. Yeah, Thursday for you guys and Friday for V-Day. But you may not want to try to end up doing both of those on the same day, but you can, it's up to you. We'll obviously be taking the test in class. So if you wanted to still come in on that same day after school or during lunch, do the retake, you could. So any questions about the schedule or timing for any of that? Yes, Sam?
For the retake, how much? Oh, no, wait, I remember. It's like it overtakes the grade that you got earlier.
Yeah, so if you do the retake, then that just becomes your grade.
Yeah, okay.
Everyone?
So how's Mr. Barlow's room, by the way?
Okay, all right, thank you. Let's see, David, I do have some papers here for you. It's still not back, and then Sam, here's some for you as well. All right. Okay, so let's go ahead and get into these notes. The first part is not really vocab, but per se, but more what we've been talking about with area under the curve. And so I just want to show you a couple pictures to be thinking about how we calculate it to make sure it's clear. I've drawn on the board over here a couple times, but not really formally in our notes. So sometimes I'll abbreviate it AUC on a rubric or something. So if you see that, hopefully that rings a bell. And if we have a graph that looks like this, just a positive slope, positive and constant slope linear relationship, we could find that area, the blue shaded part, pretty easily. It's a triangle shape, so we can use 1/2 base times height. And in this case, if we did that, we would be taking area in meters squared times depth in meters. And so what would the units be for that area? Meters cubed. Okay. And so that might tell us something about a volume relationship or something related to volume, depending on where this data came from and what it's meaning. All right. Another example, you might see something like this where you also have a nice positive constant slope, but maybe you're only trying to find the area of a certain portion. Maybe you're not trying to find the whole part. And so then you might get a section that looks more like this instead of a triangle or a rectangle or a square. It's got this other shape, and so you can use the equation for that shape, or you can break it down into a triangle and a rectangle and add them together, which is where this equation comes from. So however you want to find that area, that's also one that's pretty straightforward and probably wouldn't cause too much trouble. A lot of times students panic and think, oh, I need to know the formula for this shape, but you don't really. You can just divide it into a triangle and a rectangle and add those two together, and that's pretty easy. Okay. Yeah, Rick?
Do you divide the whole thing by 2 or just?
Yeah. And that one actually may be, they do have some geometry on here. Not that one though. So yeah, you would have to either derive that or, like I said, break it into parts and add them together. So they do though on the formula sheet have quite a bit of geometry over on this side. So they do have rectangle, triangle, circle, and then they've got some volume calculations and some trig to remind you the different sine, cosine, and tangent equations. So there is some there, but this one you'd have to piece together or remember. Now the next two slides are really not something that we're going to do like this in class. We're going to take some other strategies instead. But I want you to see it because for those that haven't had pre-calculus yet, this will be a little bit of a preview of the concepts. So if we have something that doesn't have a nice linear positive slope or even a linear negative slope where we can easily create a simple geometric shape, if we have something that's maybe quadratic in nature, then we have to think about finding the area a little differently because it doesn't make a nice triangle or a nice rectangle. We've got this curved edge. So what we can do is think about this curved edge being adding together a bunch of rectangles where we set up those rectangles where like this little part that's below the line is sort of made up for by this little part that's above. And so we're kind of getting the area, and then this little part that's above is sort of canceling out this little part that's below. And so we could take some rectangles and kind of piece them together and get a pretty good approximation of that area. And that would just be using geometry, algebra kind of logic, right? Same thing here. We can make the pieces smaller. Now in this case, they're not doing as great a job visually of trying to make up for the pieces, but if you keep making those rectangles smaller and smaller and smaller and smaller, then you start getting closer and closer and closer to the real value for the arrow or the area. And so that's what they're trying to show you with that second picture is if we keep making those rectangles smaller and smaller, we can start to get a better approximation. Now, when you take calculus, there's a couple terms, things you learn in calculus that help you do analysis of nonlinear relationships without having to take those algebra geometry sort of steps. So the two terms, and again, I'm not going to test you over these. Some of you already know what they mean and you've studied it for a while. Some of you maybe have heard of it but don't really know what they mean. You never have to use this in this course, but I want you to see the words and I want you to start to have a preview for calculus or pre-calc if you haven't been in those courses yet. That if we have a nonlinear relationship, we can use what's called a derivative to find the slope at any point on that curve. And if it's a position time graph, what does the slope tell us?
Time it took to...
Velocity,
yeah. If it's position and time, then the slope would be the ratio of position over time, and that will be the speed or velocity, depending on the concept that we're studying. So if we look at a derivative, we could find the speed or velocity at any given point by using a derivative. And then if we needed to find the area under the curve, so for a velocity versus time graph, what does the area under the curve tell us? Distance traveled, the displacement. So again, if we had a nonlinear relationship, we could use what's called an integral to find the area under that perfectly geometric shape with a curved side to it, okay? And so, again, you don't have to do any of that in this class, but I'd like to kind of introduce it at this point because for those that will be taking it in the future, or maybe if you're taking pre-calc right now, hopefully you'll see some connections as we go through the year and start to think, oh, here's how I can do the calculus. And then I've mentioned before that a lot of students have chosen in the past that if you're in Calc BC this year, or you've even finished it already, and you're doing well in this physics course, some students in the past have chosen to take the AP physics exam that is calculus based for mechanics, because the physics concepts are the same as what we learn in class, you just use calculus. And because in the calculus classes, they often use physics examples, if you're taking both classes, you usually have enough knowledge that you could actually do well in that exam. Now, I did hear from a student that it wasn't listed this year, so I need to talk to our AP coordinator and see why that is. I'm hoping they haven't made some sort of change, because I've had students take that exam every year since I've been here, and they've all done quite well. I mean, obviously, if they're in Calc BC, they're strong math students, and but if that's your scenario, you might want to think about that, and I'll be checking with our AP coordinator in the office to hopefully make sure we get that opportunity if you're interested this year. So, quick calculus preview of how what we're doing now with just algebra and geometry connects to what you can do when you learn the calculus applications. All right, so now vocab. We talk about distance all the time, and before you ever took physics, you knew the word distance and you could use it in a sentence. It's a little one of those words that's kind of tricky to define because yeah, there's so many ways we could talk about it. Like, do I mean how far I actually walked, or do I mean how far I am from where I started? And there's different things that we could get confused on if we don't make it clear which sort of change in position we're referring to. And so that's what we're trying to add clarity to today. When we use the word distance in physics, we're not just meaning any sort of measurement of any sort of distance. We're trying to make it pretty specific. And we call this kind of a measurement a scalar measurement. We're going to come back to that word in a minute. So I just put it in parentheses for now, and we're going to define it in a few slides. But distance is an example of a scalar type of measurement. Sort of the opposite of that would be a vector type of measurement. Okay. And when we talk about distance, we'll typically use lowercase d for the variable. And when we measure it, we'll be measuring it with the base unit of meters, always the metric system. Now, often, like you did in your lab the other day, you'll measure actually in centimeters, but it'll still be that metric base unit. Keep in mind, a little reminder here for your lab. I've talked to several students while you're doing the lab, and then a couple more this morning. Don't forget, if you're using a measuring device, you need to show the precision that's capable on that device. So if you were using the tape measures, the meter sticks, the dynamic rails to measure the distance so that your toy car went, all of those measuring devices have markings to the tenths of a centimeter. And so if they have markings to the tenths, you have the capacity to estimate to the hundredths. You can always estimate between the smallest markings, right? And so don't forget, if you said, well, we let the car go 20 centimeters, but you marked it exactly on the 20, then you should know that precision down to 20.00 centimeters. So in terms of recording the precision accurately in your lab report, don't forget to include those extra zeros if you made it right at 20 centimeters. Now, some of you I noticed were recording your distances in centimeters. That's fine for this experiment. Some of you were doing that in meters, also fine. Just make sure you have the same number of sig figs, whichever way you do it. So if you leave it in centimeters, fine. Convert it to meters, fine, but just have those correct sig figs to show the precision. Any questions about anything there? All right, so here's where, like I said, if we don't define what we mean by distance clearly, we can start having some debates about certain scenarios. So here we've got Dorothy and Toto. Dorothy is standing here initially and walks and ends up over here. And Toto is standing here and comes over here, sniffs around the toilet, comes over here and ends up over there. So who went farther? Sam?
I would say because of the wording, Dorothy is like who moved farther from like their initial thing. If you're saying who moved more, it would be Toto, but like who moved farther, Dorothy moved farther, technically.
Yeah, so it kind of depends on what I mean by farther, right?
Yeah.
Yeah, do I mean who had the longest path length? In that case, it would be
Toto.
Toto. But if I mean who's farther from where they started, it would be Dorothy, right? And so that's where we don't want to use words like farther, we want to use words like distance, or a new word we're going to come up with in a second is displacement. And one type is the path length that we actually follow, and one type is how far are they from where they started. Because the path length of Toto is longer, but Dorothy's farther from where she started. So we want to give clarity to our vocab so that we can be super aware of which one we're talking about. Okay, so if you're reading a test question, if you're trying to explain in a lab, you can make sure you use the right vocabulary. Now, in the experiment you performed at the toy car lab, the cars just all went straight, right? The cars never stopped and started, never turned around and went backwards while you were measuring it. They just all went straight, or at least close to straight, while they were being measured. And so in your lab, there's not much difference because they went in a nice straight line, but in other scenarios there might be. All right, so here are some key vocab words with some definitions. What I would encourage you to do is, I'm just going to be quiet for a minute or two and give you a chance to sort of read these definitions and process it a bit. Write down in your own words what you don't know. So if you know what these definitions are already, you might not need to write down very much. If it's new to you, you might need to write down quite a bit. But I would encourage you to process it and write it down in your own words instead of just copying it. Because you can copy these words without thinking about what you're writing about, and then you haven't really started the learning process. But if you think about it and try to put it in your own words, you're engaging mentally better and hopefully learning more thoroughly what they mean. So I'll be quiet and let you read it and jot down a few notes. right, so the first word, position, is just kind of a base word so we can define distance and displacement well. And the position is probably pretty clear. It's just where is the object? What is its physical location? And that's going to need to be relevant to some spot. There has to be a reference point, right? So, or relative to that spot. And so position will be where is the object. We often use X to mark the spot, and we're going to measure it in units, meters or centimeters, but that same metric unit. And distance is how far did it go along a path length. So in some situations, it's the absolute value of the displacement, but not always. Okay, it will be always an absolute value looking number. It will always be just a positive number, but it won't always be the absolute value of the displacement. So don't memorize that as that's true all the time. It's just true some of the time. So like in the examples on the worksheet 3 we did the other day, when the object was moving backward and forward, both cases, they went the same distance, but when they were going backward, the displacement would be different compared to the distance in terms of positive or negative, but numerically they would be the same. So in that case, the distance would be the absolute value of the displacement. We usually use D for distance, and we usually measure it in meters. To be honest, we rarely use distance in this course. We're almost always looking at objects moving in straight lines, and so we're almost always thinking about the displacement. In this first unit, it's where it comes up most often, where they give you a few scenarios because they want to make sure you understand the difference. But then kind of once we get past this first unit, we're almost always looking at objects going in a straight line, and so displacement's kind of what we focus in on. So displacement is change in position, but we also have to think about the direction of that change. In the end, one way to think about it is we're just trying to find the straight line distance between 2 points. If it started at point A and finished at point B, we just want to know how far those 2 points are apart. And one kind of pattern you're going to see in a lot of the equations we look at is you're going to start to see this triangle showing up. And so some of you probably have seen that before. What's that triangle mean? Sam?
So like change your displacement in.
Yeah, it's a change in something. So in this case, it's a change in position, and someone said it, what it's called?
Delta.
Delta, yeah, so it's the Greek letter delta. It's a change in position. If X means position, a delta X means a change in position. And whenever we find the change in something, whether it's position or time or velocity, that change is always going to be found as taking the final minus the initial. So a change in position, final position minus initial. And another thing you're going to be seeing a lot as we get into several equations over these next couple weeks is little subscripts on the variables. And the subscripts just give us some information. When we're looking at a displacement, that means there had to be 2 different positions, and so there needs to be a final and initial. Sometimes you'll see F and I for final and initial. That's kind of more typical for College Board usage. But sometimes I might do an example where I do like position 1, position 2, position 3. So I might like have X1, X2, X3 if there's more than 2. So you can use whatever subscripts make most sense to you, but you'll start to see those showing up in a lot of different equations. Sometimes instead of I, you'll also see a 0, like X0. Where was it at the 0 point in time kind of idea. All right, any questions about these words? Position, distance, or displacement? To make sure the definitions are making sense, we're going to compare them with a few examples and see if you can pinpoint the difference here. All right. So let me get this out of the way here. All right. So displacement, we just kind of defined it. Here they're sort of wrapping it up, making sure you didn't miss anything on the previous slide. So we've talked about position, and we've talked about how a change in position is referred to as displacement. We even looked at this little Greek letter delta and talked about how that means change in. So when you see that, so it's kind of just summarizing a few things here. So when you see delta X, it means you're changing where X is or changing the position. So kind of a little summary here of what we just saw on the previous slide. So if you look at how you wrote your notes down, maybe you had something a little bit like this. Just a different way to word it, different way to say it, and some clarity on what that triangle means. All right, we said it, but now it's also visually in front of you. So let me give you an example of displacement versus distance, and then we'll have you practice a few. So displacement describes how far you are from where you started and the direction in which you traveled, no matter how you got there. Again, another way to word it. It's the same definition, worded in a different way. So maybe this matches more the way you put it down in your notes. Let's say that we decided to go on to a field trip and we're driving and we don't live where we live now. We live out in the East Coast. So we decide, hey, we're going to drive from Pennsylvania to New Jersey. We drive 60 miles towards New Jersey from Pennsylvania. We stop, maybe we have dinner and we start coming back home. We drive 20 miles and realize, oh, I'm kind of low on gas. So I'm hungry again. So you stop at the gas station, fill up the car, maybe get a Coke and a candy bar. And so at this point, how far have we driven? 80 miles. But how far are we from where we started? 40 miles. All right. So what's the distance that we've traveled?
40.
The distance is
80.
80. We've actually traveled a distance of 80 miles, but our displacement is 40 miles east of where we started. Okay. Right, so-
Displacement is how far from your distance is how far you actually did.
Yeah, distance is path length. Displacement is how far are we from where we started. So we traveled a total of 80 miles distance. That's what the odometer on the car is going to say, and that's what's going to dictate how much gas we used. But we're only 40 miles from home, and so that's our current displacement from the origin. All right. If we wanted to think about, the calculation or the formula, how it fits together, our displacement, our change in position is our final position minus our initial. Our final position is at the 40-mile mark. Our initial position was at the 0-mile mark. 40 minus 0 is 40. Okay. So you could think about it kind of more visually, or you can think about it more as an equation. But that's the distance, displacement, the difference between the two with an example. Making sense so far? We okay with that idea? All right.
Oh wait, can you go back?
Yes.
Okay.
Got it? All right. All right, so when we measure distance, we're only ever going to use positive values because we don't really care about the direction. We just want to know how far did we go. So for the 80-mile distance that we drove, we don't say 80 miles in what direction because we were actually going multiple directions. So we just say, well, we just drove 80 miles. Okay, so the direction doesn't matter. It's always going to be a positive value. You can't travel a negative distance. Right? Distance is just the path length. You can't travel a negative path length. You can be negatively positioned from where you started, but you can't travel a negative path length. If I move one step, that's a positive path length, right? I've moved in some direction. So it's got to be larger than 0 for distance.
So like when we do like the calculations for distance, like we'll never get a negative value, right? Like if we did, how would, or that would just like not work?
Yeah, so if we're really talking about distance, the actual path length, then it can't be negative because if I go right, left, like I'm still adding steps, I'm still adding meters, right? And so there's no way to get a negative distance for me because it doesn't matter which direction I go. But if we have negative numbers, then we must be actually talking about displacement because then all I care about is where did I start and where did I end. And so if you start to see negative, and that's actually coming up on the next slide, is if you start to see negative numbers, then, oh, we must not be talking about distance anymore, the path length. Now we're talking about displacement. How far is point A to point B and in which direction? All right, so let's go on to that. So displacement then can be positive or negative because if we're only thinking about the change from where we started to where we ended, if I started here and ended there, my displacement is positive because I'm moving in the positive direction. But if I started here and ended there, my displacement is negative because I'm moving in the negative direction. So distance, we don't care about the direction. We just know how far did you actually move. Displacement, The direction is critical. We have to know the direction, and we have to know where we started and where we ended. In fact, that's all we need to know. And we can calculate that displacement taking the final position minus initial. All right. So one thing about this particular curriculum, there's been some research done that most students need to process a concept a minimum of 7 times before they actually start to fully understand it. And so that's one thing that they do in this is they'll define it 3 or 4 different ways, and they'll try to show you 3 or 4 different examples, trying to make you process it at least 7 times. That's kind of their goal. So sometimes it might seem a little repetitive. I wouldn't encourage you to try to write down everything you see, because you'll be writing down multiple definitions just reworded in different ways. But it's good to see it, it's good to read it, it's good to hear it, it's good to process it. Hopefully, the goal of the design is that you end up having to study less later because you've seen it so many ways as we've processed it together. We don't have time to do it for every concept, but for the things we do, that's their goal. All right, so questions for you. When you know the answer, raise your hand. How far your ending point is from your starting point is known as A, distance, B, displacement, positive integer, negative integer. Okay, what do you think, Claire? Distance. How many of you agree with A, how far you are from the starting to ending point? Not too many people agreeing. So what do you think, Jerry?
I'm agreeing.
Oh, you were agreeing. Okay, so you two agree. Anybody else agree? Okay, so who thinks something else then? I saw a bunch of people raise their hand. Dexter, what do you think?
Displacement.
Displacement? Okay, how many agree with that? All right, yeah, displacement is just final minus initial. How far am I away from my initial position? So we should choose B. All right, let's keep practicing. A car travels 60 meters to the right, then 30 meters to the left. What distance did the car travel?
90.
Yeah, let's raise a hand so we get everybody a chance to think about it first. Okay, so do we agree with 90 meters?
Yes.
All right, so the distance traveled is actually 90 meters, right? We're taking, well, we went 60, we went 30, total of 90. All right, you travel 60 to the right, 30 to the left. What is the magnitude and direction of your displacement? Think about that. Don't say it, just think about it for a second. Raise your hand when you know. Okay, Annie, what do you think?
30 meters.
Sorry?
30 meters to the right.
30 meters to the right. And I saw Sarah, thanks for raising your hand there too. Glad you're following along. All right, we okay so far? Making sense?
Yeah.
Couple more. All right, raise your hand when you know. Starting from the origin, the car travels 4 kilometers east and 7 kilometers west. What's the total distance? Don't say it, just hold it in. Patrick? 11 meters is the distance. All right. Starting from the origin, the car travels 4 kilometers east and 7 kilometers west. What's the displacement? Eddie?
A.
Sorry?
A.
3 kilometers west, do we agree?
Yeah.
Everybody confident?
Yeah.
All right, good job. All right, you run twice around a 400-meter track. At the end of your run, what is the distance you traveled?
800.
Say it out loud. 800. You run around a 400-meter track 10 times. At the end of your run, what's your displacement?
0.
Say it out loud.
0.
0. All right, so that's why I don't run. I mean, if you're just gonna end up where you started, like, why do that all that work and you got to go anywhere?
I can't really,
Yeah, that's definitely
At
not.
least that's my
I
excuse.
love running.
Ew.
Why would you do that to yourself?
All right, so
That's why you sweat.
early on in these notes,
I'm just walking.
I didn't know.
Okay, yeah, I was like.
early on these notes, we saw the word scalar and then vector, and now we're gonna actually define them. So some types of measurements that we make are vector values, meaning they have a numeric magnitude. Magnitude just means size, so it has a measurement, it has an actual number value. But they also have a direction, east, west, north, south, forward, backward. There's some direction associated with it, right? So the kinds of measurements we call vectors have both concepts, a numeric magnitude and a direction. Scalar values of measurement just have a magnitude and we don't care about the direction. So we've talked about two. We've been talking about displacement and distance. Which one do we care about the direction? It's the vector, but is it displacement or distance? Displacement. The direction matters, right? For distance, all it is a path length. I don't care what direction I went. I just want to know how many steps I took, how far did I go, right? But displacement, I need to know, well, where was I when I started? Where was I when I ended? Was I going positive? Was I going negative? The direction matters for displacement, right? So our first pairing, we're going to see displacement is the vector and distance is the scalar. And as we said before, displacement can be positive or negative because we might be going forward or backward. We might be going up or down, right? And so we can have both positive and negative values for these vector measurements. Displacement's the one we've been focusing on. Distance, always a positive value. It's sometimes the absolute value of the displacement, but it always looks like an absolute value numerically because it's always positive. All right, some other examples. Velocity and speed. Now in your lab, I mentioned the other day, you could kind of use those terms interchangeably in our experiment because the car was always going forward at a constant rate. So the displacement and the distances would be the same. And therefore, as we're going to define here very briefly, the velocities and the speeds would be the same because it's always going straight and it's always going forward for our lab. But velocity is the vector value of that measurement. When we give a velocity, we want to tell what's the numeric value, 3 meters per second, and then what's the direction, to the right or forward, something like that. Speed, we don't really care about the direction. We just need to know the value. And again, for your toy car lab, those two are going to be interchangeable. All right, some other examples. This is going to be important in Unit 2, mass and weight. Weight is a force, and weight would be towards the center of the Earth. It's caused by the gravitational force field of the Earth. Mass is just how much matter our body's made up of, or our object is made up of. And so mass isn't directional, it's just how many particles are making up this object, how much material is there. Weight is what's the impact of gravity on me, or what's the impact of gravity on this object. And gravity always pulls to the center of the Earth, so it has a direction. SM?
So wait, so like for like a lab or like anything, we would want to get the scalar values over like the vector values because like again like mass, you use mass instead of weight because weight is like affected by multiple factors. So like all of these other ones are like raw data. So then if you want it, so does that mean we would want to get like scalar in like a lab or anything in comparison to vector?
It really depends on what we're trying to accomplish in the lab. So sometimes knowing the vector value will be more important because maybe the direction is important for what we're trying to study. Sometimes maybe the scalar value would be more important or more applicable. So it's kind of hard to say that either one would be more or less valuable all the time. It kind of depends on the nature of the experiment. All right, the next two, these two don't really go hand in hand precisely, not like distance and displacement go hand in hand, velocity and speed go hand in hand, weight and mass go hand in hand. Acceleration time don't necessarily go hand in hand, but acceleration is a change in velocity. And since velocity is a vector, and if it's changing, that's how we determine acceleration. That's going to be the focus in Unit 1B coming up starting next week. We'll start to nibble into that a little bit more. And then time is always just moving forward. We can't stop time, we can't go back in time, it's just moving forward, so it's always going to be a positive value. It's going to just be a scalar measurement. Okay? So, questions about the idea between a scalar and a vector? All right, next couple of slides I'm going to go through pretty quickly because it's just talking about time, and then we'll slow down a little bit more when we get to speed and velocity. So time is one of the things that we're going to be measuring often. You measure the time in both the labs that you've done so far. And when we measure it, we'll be measuring it in seconds almost always, because we're going to be looking at very short time frames. And we'll use the variable lowercase t for regular time measurements. Now, we used capital T on our first experiment for what? What would that capital T stand for? It was a measure of time, but we gave it a specific word. Yeah, period. So when you see a capital T, it's also time related, but it's called period. So it's like, how much time does it take for a pendulum to swing over and back? So it's still a time measurement, capital T, for what we'll be using for, but it is a little bit of a different focus. So for almost everything, we'll be talking about not something swinging, usually be talking about things moving in straight lines. And so we'll usually be using lowercase t. This video I'm not going to take the time to show in class, but it is on Axis. It's kind of a neat little video. It's about 1.5 minutes long, and it just talks about how we often interchange the words distance and time. For example, if someone says, how far do you live from school? I might say 10 minutes. And I answered time, but they asked me distance, right? So we often interchange those things because we think about them together, hand in hand, so often. And so it's just kind of a clever little video that talks about that. Now, when we think about time and we're measuring it in lab, we have to think about kind of two types of measurements. We might need to know how much time passed from when I dropped the book until it hit the table, or we might need to know what time was it when it hit the table. And those would be two different measurements, right? We might need to know how long did it take me to move the book from here to there, or we might need to just know what time was it when the book was in this position, all right? So there's two ways we sort of measure and think about time. We'll normally be thinking about an instant in time or a clock reading. What does the stopwatch say? What was the time right now? An instantaneous moment. But then there will be other times where it's more important for us to not think about just that moment, but how much time elapsed. And so you might see it called elapsed time or time interval or the change in time. And because it's a change in time, you see the triangle showing up again. And whenever we find a change in anything, we want to take its final value minus its initial value. Now, a lot of times, numerically, these two things will be the same. If I'm using a stopwatch, it usually starts at 0, right? And so when I stop it, that's the instantaneous time right when I ended the measurement. But it's also the elapsed time because it started at 0. So it's actually telling me both, right? So often the numeric value of the instantaneous clock reading is also the value or the magnitude of the time interval. But it's important that you're careful when you're reading the questions because sometimes they want to know position at a particular time, an instant. Sometimes they want to know a change in position over a change in time. And so you just have to be careful in the way you read the questions that you know if they're talking about instantaneous or an interval. All right, so let's get to the last bit here, speed. Speed is defined as the distance traveled by the time it took to travel that distance. So nice little background information for your lab, right? You've got a lab report you're pulling together. Background, you're finding speed in the lab. So here's your definition, here's your equation. Now, distance and time we kind of consider more fundamental measurements of nature. Where is this object? How far did it move? How much time elapsed? But speed is a ratio. And a lot of the things we're going to be talking about, speed, velocity, acceleration, a lot of things we talk about are going to be ratios. All right, we good on that one? When we measure speed, we're not going to usually measure it directly because we don't have speedometers or radar guns. We're normally going to be measuring the fundamental distance and time and calculating it, right? There are instruments out there that can measure speed directly. We do have some motion detectors, and so We will use those occasionally where you can actually get a velocity reading immediately. But often we'll actually be measuring the distance and the time and calculating the speed. All right. We've seen in your toy car lab how many measured in centimeters for your positions and distances? Pretty much everybody. Okay, great. If you want to keep your speeds in centimeters per second, that's fine for that experiment. You don't have to change it. But when we start doing calculations moving forward, most of the time moving forward, you're going to want to make sure you always convert to meters. Because especially once we get into free fall and thinking about gravity, there's a number we're going to be using, 9.8 meters per second squared. And your units always have to match. So for this experiment, because of the simplicity of it, centimeters per second is fine. But starting in the next unit, you'll probably always want to convert to meters just so that it helps process your units properly. All right, so let's go back to Toto and Dorothy. If this is that same scenario, same path, and we see that they both started moving when we clicked the stopwatch, and when they got to their final positions, they got there simultaneously 9 seconds later. So who was faster?
Well, hold on.
Yeah, initially the thought is probably Toto. Toto had to be moving faster because Toto went farther. But what if I say Toto went farther, what am I talking about? What kind of farther?
Just in general, the distance.
The distance, the path length, which would then be the speed, right?
Yeah.
But what if I don't care about the path length? What was the other measure?
Velocity.
Yeah, velocity would be the displacement. So I could be thinking about this two ways. Am I thinking about it, who is actually moving at a more rapid pace along their path? Or do I mean who got to their final position faster and how far did they go? It's different depending on whether I'm talking about speed or velocity. So if I'm talking about the path length, the distance, well, Toto had a greater distance of its path length. So therefore, Toto would have a greater speed. But velocity is based on displacement. Okay, well, displacement is the straight line distance. Well, Dorothy had a bigger displacement in the same amount of time, so Dorothy had a greater velocity. All right, so again, in your toy car lab, it didn't matter because the cars were just going straight. But in scenarios like this, where not both objects are going straight, you have to understand the difference between the two. Now you'll see another little symbol here, this little arrow above the V. When you see an arrow above a variable, that means it's a vector. And what do vectors always have to show? Direction. And so it's just a reminder, hey, what is the direction of this vector? So whenever you see a little arrow above a variable, it's a reminder. A lot of times books won't include it, but if you see it, it's just a reminder, oh, that's a vector value. I got to make sure I give that direction as well as the magnitude. All right, so just like we have to clarify, what do we mean by farther? Are we talking about distance or path length? Or do we mean displacement from point A to point B? That carries over to speed, which is distance over time, versus velocity, displacement over time. So like I did before, here are some definitions for you. Think about it, jot down what you think is going to help you remember it well.
Is the year regardless, is that like regardless?
Means we don't care about the direction.
So usually like position, gives you velocity, right? Or like the derivative gives you velocity, right?
If you're looking at position time graph, yeah, it would give you the instantaneous velocity.
Not the instantaneous speed.
Most likely they would be equivalent. Yeah, because if you're looking at an instant, the direction is not changing in an instant. So magnitude wise, they would be the same. So the only difference would be if you're calling it speed, you would just give the numeric value. If you're calling it velocity, then you would say in what direction was it moving. But numerically, they would be the same in an instant.
So, like the accurate equation for speed would be distance over change in time, not just like distance over time.
That's okay to say distance over time.
Okay.
Often you'll see, even College Board, they often leave the delta off of time.
Okay.
So sometimes they'll put it on position, or sometimes they'll just do like final XF, XI. So, but often for time, they do drop off the triangle, drop off the delta. Just like we mentioned before, usually the clock reading on the stopwatch is also the elapsed time, because most of the time we start the stopwatch at 0. So because of that, they will often drop off the triangle.
Can I drop off the triangle in half?
Yeah. Whatever College Board allows, I allow. So what they don't allow, I don't allow. I try to follow their leads so that you're well prepared for the exam. So the key here is, again, just making sure you know speed is all about distance compared to the time elapsed. Velocity is all about displacement compared to the time elapsed. And we might be talking about an average, or sometimes we need to know an instantaneous. And so again, it's where you have to read the questions very carefully. Do they want to know just the average velocity from when they left home to getting to school? Or do they want to know the exact velocity when you were getting on the on-ramp? Like, what is the question asking about? And sometimes they might want it at a certain time. Other times they may just want to know the average. And so just have to read the question carefully to make sure you're answering what they're asking. Yeah, Britt?
And change in time is final time minus initial time.
Yeah, anytime you see that triangle change, you can substitute final minus initial, whether it's time, velocity, position. You can always just substitute right away final minus initial. All right, last little thought here. We got a tortoise and a hare. The tortoise is walking forward at 0.1 meters per second on a train that's moving 30 meters per second. The rabbit is on the ground beside, moving 5 meters per second. Who's moving faster?
Turtle. Well, hold on.
Technically, the turtle. Because
Yeah,
he's
'cause
physically moving
it's-
faster.
Yeah, the turtle.
Body is.
What is not the turtle? Sorry, or
Do you guys realize I'm asking you some really terrible questions today, right? Like, who's going farther? I don't know, Mr. Webb. What do you mean by that? Who's going faster? Mr. Webb, come on. What do you mean by faster?
do you mean individually faster, or do you mean like faster?
And here I'm asking you another poor question. What clarity do I need to give you?
Rapid.
What is
By like the
faster
individual,
and
you mean
possible?
considering.
Yeah, go ahead and say that again, Tuck.
Which one is stand there not moving to the ground?
Yeah, are we talking about relative to the ground? Are we talking about relative to the train? Like, which one is it relative to? I need to give you that information so you can answer. Which one's moving faster relative to the ground?
The tortoise.
The tortoise. Which one's moving faster relative to the train?
The hare. The hare got like
rabbit.
rabbit to the train.
Rabbit. Which one's moving faster? Too general of a question, right? I need to specify what are we talking about here? Like, if we saw these two beside each other, the turtle's going to get wherever it's going faster, right? Because it's on the train, even though relative to the train, the turtle is moving very slow. Relative to the ground, the turtle is moving really fast, right? All right, so we have to know a frame of reference. And so we're going to come back to this concept in the next unit, but I like to just begin to introduce it here. Have you guys ever been sitting in a car and you know you're parked, but the car beside you moves and you like jerk because you think you're moving? Have you guys ever had that experience?
Wait, say that again?
So you're sitting in the car and you know you're parked, but then the car beside you move, you see it out of the corner of your eye, and just for a second, you think you're moving, right? Yeah, so most of you have felt that way. There's, we see that movement relative to where we are, and sometimes it gives us a little shock. When you're driving down the highway, if you're got the cruise on 65, you're a good law-abiding 65, staying right on, I saw that smirk. Okay. You got a 65 going straight on the speed limit. If a car goes by you really fast, what do you know about it?
Faster than 65.
Yeah, it's going faster than 65, right? So what if you look over and the car looks like it's not going anywhere?
Same
It's
speed.
going the same.
Same speed as you.
Relative.
Yeah, what if it looks like it's going backwards?
And it's going the wrong.
Oh,
okay.
If it's facing forward but looks kind of like it's going backwards out of the corner of your eye, it's going slower than you. So that relative position is important when we think about the relative speed of things, right? Are we speaking relative to the ground? Are we speaking relative to one another? We have to be careful about that. All right, a couple questions to finish up the lecture here. Car travels at a constant speed of 10 meters per second. This means the car, and for this one, don't say it out loud, but just raise your hand when you think you know it, increases its speed by 10 meters every second, decreases its speed by 10 meters every second, moves with an acceleration of 10 meters every second, moves 10 meters every second. Joaquin, what do you think?
Moves 10 meters every second.
D, how many agree with D? All right, yeah, so the first three are all talking about a speed that's changing, right? That's acceleration. We're gonna get to that next week. All right, a rabbit runs a distance of 60 meters in 20 seconds. What's the speed? Go ahead and say it out loud.
30 meters per second.
3 meters per second.
What rabbit is that?
An airplane on a runway can cover 500 meters in 10 seconds. What's the average speed? 50 meters per second. All right, just some mental math. A car travels at a speed of 40 meters per second for 4 seconds. What's the distance it traveled?
160.
Yeah, we have to think about speed is distance times time. So distance would be speed, or sorry, speed is distance divided by time. So distance would be speed times time. So we get 160. You travel at a speed of 8 meters per second for 6 seconds. What distance did you move? 48 meters. All right, so we can use that speed equation to solve several different kinds of questions. And then finally, you travel at a constant speed of 6 meters per second. How much time does it take you to go 120 meters?
20 seconds.
20 seconds. You travel at a constant speed of 5 meters per second. How much time does it take you to go 150 meters?
30 seconds.
30 seconds. All right, just some good, quick mental math to make sure you're processing it. All right, so for the last time here we have remaining, you can get with your partners and you can work on writing up your lab reports and getting your graphs done and doing your extension questions. You can also show me the corrections on the pendulum lab if you need to get those checked off if you haven't done that already. And so use your time well.
Can I use the restroom? Can I go to the restroom?
What is this?